Hello and welcome to my video, lesson 5.2 on the photoelectric effect. So the photoelectric effect is another piece of evidence that we have that light comes in discrete packets called quanta or photons. And we looked at yesterday the ultraviolet, or the last lesson I should say, the ultraviolet catastrophe, which is this idea of black body radiation showing that light must come in discrete packets. But here's another effect or another experiment we can do to show that effect taking place. Essentially what we have is light hitting one end of a set of parallel plates in a circuit. And so these parallel plates are not touching each other. This over here, what I'm doing right now, this part is the red wire, and then these are the parallel plates on either end. And so what happens is the light comes in and hits one of the two parallel plates, and depending on the type of light, we will have electrons being ejected from that piece of metal. So what happens is it depends on the type of metal. Some metals are happier, quote unquote, to lose electrons, such as alkali earth metals like sodium and potassium. And that's more of a chemistry type topic, but you can take a look at the periodic table of elements to see which ones are happier to give up electrons. Essentially, the periodic table looks like this, roughly, and all of these ones in this column, these ones are all pretty happy to give up electrons. And actually, the further down they go, the happier they are to give up electrons. All the rest of these in here, maybe I'll use blue to show that. All the rest of these, they're there's different reasons for some being stronger and some being weaker. P, D, S, orbital, stuff like that. There's interesting stuff there. But I'll say that this second row, which is here in green, those ones are also pretty good at giving them up, but the most important is those red ones. Or maybe I'll make that pink. The pink ones here are the alkali earth metals, and those ones are happiest to give up electrons. Okay, so essentially that's what it is, and different metals will be more or less happy to give up an electron, so it depends on the energy of the light coming in. If you give the element enough energy, then it will eject an electron. Now, what you'd expect normally is that as we increase the intensity of the light more and more, so literally just turn up the wattage of the light, more electrons would be released, because turning up the wattage means we've added more energy per second. Even if it took some time, we'd expect the energy to build up inside the metal, and eventually electrons would start to be released. However, we don't see that happen. The photoelectric effect really only takes place if you get past a certain threshold. So let's take a look at a simulation that will show the photoelectric effect. This is a PhET simulation, and we're just going to see how this looks right now. So essentially what we're doing is we have different types of metals. So here we're going to have copper. And copper, if you drag the intensity up to 100%, and we're at 508 nanometers, this is green light, we can see that nothing is being ejected. But if you go to sodium, sodium is a type of metal that will be ejecting electrons at that wavelength. So it doesn't matter the intensity, even if I lower it quite a bit, it's just going to shoot less electrons, or less often, because there are less photons hitting it. But it's still each photon individually, and that's the key. Each photon individually has enough energy to release an electron. So we'll put it back up, and what we're going to do is just adjust it until nothing is released anymore. So 541, nothing is released. 532, something is released. So let's try 35. Stuff is still released. So let's try 38. Is stuff being released at 38? Yes, it is. Slowly, but it is being released. What about 39? Yes, very, very slowly, and you can see these electrons are barely moving now at 39. And then let's try 40. So 540, will anything be released at 540? And I think you can see here that nothing is being released at 540. So what you can see is that for sodium, we have found the wavelength of light that will allow electrons to be released. So what we've just discovered is the work function of sodium. That means the amount of energy per photon to release one electron. So one photon releases one electron, and that is the key. You can't double up photons to electrons. So each photon individually has to have enough energy. Now if we switch this to copper, you're going to see that nothing is being released anymore. And that's because different metals have different work functions. So sodium has 539, but copper, I think, is going to be in the ultraviolet. Yep, we're into the ultraviolet quite far now. Oh, and somewhere over here, it is releasing some over there. So let's see if we can maybe say, whoops, I made a mistake. That's okay. 258. Is anything being released? Yes, it is. 265. Is anything being released? No, it's not. 260. Yes, things are being released. 261. Still being released. 263. Very, very slowly. 264. And it looks like we've found the work function for copper, 263 nanometers. So every material will have a different work function. So what does that exactly mean? Because the intensity doesn't change. Just the wavelength is what's necessary. So when we find that wavelength that can just barely release electrons, that's the work function. That's the amount of energy per photon that can release the electron. And this is hard to measure empirically because we can't fine-tunely adjust our wavelength as we did in this here. We can't fine-tune it that well. But let's say we're doing sodium and we have a purple laser pointer. I think my laser pointer is somewhere around 380. So you can actually use a purple laser pointer and shine it at sodium, and electrons will be released. And what you can do is you can measure the current right here, and that tells you something about it. But more interestingly, what we can do is we can now adjust our voltage to match. So what we're going to do is just slowly adjust this voltage so that with the two parallel plates we can balance them and make it so that the electrons never reach the end. So we're going to, we need to increase the voltage, don't we? Yeah, that's pretty good. So we're pretty close to our stopping voltage. So in real life, what you could do is just adjust this a little bit. So maybe what we could do is 9.8. Oh, that should be a negative. Okay, and so let me just explain what we got here. We got a result that's pretty darn good. I just want to keep adjusting it, making it perfect. But what we're looking for is the perfect voltage to just barely stop the electrons from reaching the other plate. And what this voltage is going to do is it's going to make this current zero. So the current you can read there is 0, and because that current is 0, that's why we know we have put enough voltage on these parallel plates to stop the electrons. Now, this stoppage of electrons, we call this, surprise, surprise, the stopping voltage. Essentially what we're doing here is we are basically doing the same thing as if we were throwing a ball up in the air and it was coming back. So we were looking at how much energy it got up here, which in that example would be mgh, and then using that we can find our kinetic energy down here, a half mv squared. So we can convert between one and the other. Okay, that's essentially what we're doing. Now, this is great, but in our example, instead of the EP being gravitational potential, in this case it is the electric potential. So we're comparing the two, and we're saying this is the voltage required to stop the electrons from actually reaching the other side, and that's why those two are equal. One is initial, one is final energy. So that's what we have there. It's the kinetic energy of the electrons themselves. If you wanted to find, you could find the velocity of the electrons, but it's not really necessary. But what you can do here is, now that you know the kinetic energy, if you also know the work function, you can find, or if you know this, and you know what the wavelength of light is, then you can work backwards to find your work function, or vice versa. Alright, so here are the first two questions. So I recommend you pause the video now and try them out yourself. Alright, example 1. What is the maximum wavelength of a photon needed to release an electron of an element with a work function of that? So the work function is 3.2 eV, which means that we're looking for, right now we're looking for that frequency, but what we're looking for is, if we're looking for the maximum wavelength, we have to change this from frequency to wavelength. So it's going to be C equals lambda F, so it's going to be C over lambda equals F. So let's put that back in here. So actually let's go HF naught. So let's put that in. So it'll be W equals H. Instead of F naught, we're going to do C over lambda. Okay, and then we're going to solve for lambda. So it's going to be lambda equals HC over W. So lambda equals, and so we get an answer of 3.8 times 10 to the negative 7. 0.888 times 10 to the negative 7 meters, or another way to write that is, actually, let's just leave it like that. It's almost a nanometer answer, but then we'd write like 390 nanometers, which then tells us 3 sig digs, and this says 2, so yeah, it is what it is. Let's just leave this answer here. Alright, let's try the next question. And again, we have 3 questions here. I recommend you pause the video, try it yourself, and see if you get the right answer. Okay, what is the maximum energy of the electrons if they're stopped with a potential of 4.5 volts? So that means kinetic energy equals Q and then V stop. Well, all we got to do is plug those in. So 4.5 times oh yeah, and we could go like 1.6 times 10 to the negative 16 if you wanted to get joules. But instead of doing joules, we can just do it as EV. So 4.5 EV. And that is the nicest way to answer this question. So if it's just one electron, the charge is just one elementary charge. And so 1 E times the V, so 4.5 EV. Okay, example 3. If a mystery metal plate is used on a photoelectric setup, given the stopping voltage of 0.2 volts and the light incoming is 380 nanometers. What is the work function of this metal? So this is a more realistic setup where you're seeing this effect taking place. So stopping voltage, just barely stopping the electrons from making it to the other side. So that means that the total energy, okay, I'm going to write it out kind of more generically. Total energy is the electron energy plus the work function. Okay, that's the basic idea here. So the total energy is given by the regular HF or HC over lambda. So the normal formula, which is E equals HF or HC over lambda. So that's the normal calculation of the energy of a photon. Okay, the energy of an electron is given by that stopping voltage, and the work function is given by HF naught. Or actually, we don't even need that. We're just looking for W, the work function. So we can now rearrange this to solve for the work function. So it's going to be W equals HC over lambda minus QV stop. So what we get is 3.06. Our stopping voltage was only 1 sig dig, so that's kind of a problem, but let's just say 3.1 EV. And I'm going to change the stopping voltage so that it gives us 2 sig digs. Alright, I hope this video helps you better understand the photoelectric effect and how to use some calculations in it. Hope the video helped, and good luck.